One more thought on linearization and differentials. In blue, I have a function graph y equals f of x, and in red, I have its linearization at the point a. If y equals f of x is differentiable at x equals a, and x changes from a to a plus delta x, then delta y in f is given by delta y equals f prime of a delta x plus epsilon delta x in which, and then I have a few more things to fill in. But I thought we'd talk about this equation first, because I recognize this, the change in y. In fact, in my diagram, I could go on and fill that in, right? A has changed from a to a plus delta x, and then the change in y is the total rise up to that function. So in blue here, that entire distance, I would call that the change in y. This expression on the right-hand side, just this first part, the first term, f prime of a times delta x, I recognize that as the differential. I'm used to seeing this as f prime of something times dx, but then I realize that dx is an independent variable, and I can simply choose it to be the value of delta x, that increment on the x-axis. So my differential is just this amount, how far I've gone up to my tangent line. And in a previous video, we said that when we have a differentiable function, when my linearization is doing a good job, dy can be used to approximate delta y. These values should be close. And now I see the role in this last part. It's the error term. It's how far off the two things are, and I see it in my diagram. It has to be this amount, epsilon times delta x. That if I take dy and then epsilon plus delta, epsilon times delta x, I get the total change in y. Now the important thing, the thing I haven't filled in yet, is that epsilon goes to 0 as delta x goes to 0. And what that is saying is that if I let my interval on the x-axis get smaller, the difference between these two things, delta y and dy, gets smaller and smaller. That if I let delta x go to 0, the epsilon I'm multiplying this term by also goes to 0. The error gets smaller and smaller and smaller. So what this is really saying is if I am differentiable at a point x equals a, then my linearization does a good job of standing in place of the function, and does a better and better job as delta x tends towards 0. That if I stay really close to a, my linearization looks a lot like the function. This can actually be taken as a definition of what it means to be differentiable at a point. And for those of you who are going to go on and take more math classes past this, when you get to higher dimensions in Calc 3, a definition like this is what we have to use to define differentiability.